Hello everyone. So in this session, I'd like to explain the Maxwell's equations. These are fundamental equations for electromagnetism. So we have used many weeks to derive this Maxwell's equations. So this is a summary of the Maxwell's equations. Gauss's law for the electric field is expressed the surface integral of the electric field is equal to 1 over epsilon sub 0 times the charge. So charge is equal to using the charge density of the law integral over the volumes. So this is a Gauss's law for the electric field. Gauss's law for the magnetic field. Magnet, there is no monopole. So surface integral of the magnetic field always becomes 0. This is a Gauss's law for the magnetic field. Ampere's laws. So I introduced the displacement current derived by the James Maxwell. So line integral of the B over the crossed path is equal to the mu sub 0 times two terms. First term is the current densities integral over the cross surface plus epsilon sub 0 derivative with respect to time and the surface integral of the E over the surface. And the Faraday's law is a line integral of the electric field over the crossed path is equal to the partial derivative with respect to times the surface integral of the magnetic field. This is the Faraday's law. So these four equations is a fundamental equations of the Maxwell's equations. So also I'd like to show you the expression in the differential forms. First expression is the Gauss's law. Del dot E is scalar product of the del and the electric field is equal to the charge density of rho over epsilon sub 0. And del dot B becomes equal to the 0. This is the Gauss's law for magnetic field. And the next one is a del cross E. So you can express the curl E is equal to minus round B round T. This is a Faraday's law. Last one is a curl B, is a del cross B equal mu sub 0 times I plus epsilon sub 0 round E round T. This is new Ampere's laws. Last term corresponds to the displacement current. So by looking at these equations, a time-varying field of the either kind induces a field of the other kind in the neighboring region of space. So for example, by having the non-zero time derivative of the B with respect to times produce the electric field. And also the time varying the field of the electric field produce the magnetic field. By looking at these equations, you could imagine the propagation of disturbance. So this is electromagnetic waves. So electromagnetic waves, we are going to study that in the next lectures. I'd like to show you the complete set equations in the classical physics. So in this lecture series, I derived the Maxwell's equations, these four equations. Gauss's law for the electric field, Gauss's law for the magnetic field, Faraday's laws, and Ampere's law. I explained the Lorentz force due to the electric field and magnetic field. So if you consider the particle with charge, electric field and magnetic field is acting on the charged particles. And another important force is the gravitational force based on the universal law of gravitation. So G m sub I m sub j over r sub I j cube times r sub j minus r sub I vectors. The motion of the equation based on the Newton's equation motions. In this case, we just only consider the momentums of the particle with the I. So dp sub I over dt is equal to the force acting on these particles due to the Lorentz force and the gravitational force. So by solving these equations, we could follow the motion of the particle of the eye. But the gravitational field and electric fields also created by the particles. So to find out this E and B, you have to solve the Maxwell's equations. And the motion of the particles produce the current. These are really complicated equations. All the terms is coupled strongly with each other. So it's really complicated to solve these equations at the same time. I could show you the basic equations we need to solve in the framework of the classical physics. This is the end of today's sessions.